We have a capacitor here. We want to find the voltage across that capacitor for t greater than 0 after we move this switch from position A to position B and this 2 amp source is connected to the capacitor. Since we're interested in t greater than 0, let's redraw the circuit to show the switch in the correct position. So this circuit has one energy storage element. It's a capacitor, so that means this is an RC circuit, which is first order. So it's going to be governed by a time constant. That time constant is going to be the equivalent resistance seen by the capacitor times that capacitance. Likewise, it has a constant input. So for a first order circuit with constant input, the solution form is going to be some constant, e to the minus t over tau, plus some other constant. Since tau is equal to the equivalent resistance seen by the capacitor times the capacitance, it's probably easiest to determine the equivalent resistance to get a number for tau. So to find Req, kill the sources. The current source becomes an open circuit. I have a 6 ohm resistor. These are the capacitor terminals, a 3 ohm resistor, and across these terminals is where I want an equivalent resistance. No current goes through an open circuit by definition, so any current going through here also goes through here. You can verify that by doing KCL here or here. So these two elements are in series, and Req is 6 plus 3 ohms, or 9 ohms, and tau is equal to 2 times 9, or 18 seconds. Now we get K1 and K2 by applying initial and final conditions. So to get our initial condition, we need y at t equals 0 plus, but we don't know anything about that unless we invoke the fact that a capacitor voltage can't change instantaneously. So what we're actually going to do is find y at t equals 0 minus. So at t equals 0 minus, if the switch has been in this position for a long time, the 2 amp source is not connected to the capacitor. So 2 amps just goes in its own little loop over here, and the capacitor isn't connected to an energy storage element. If the switch has been in this position for a long time, the capacitor will look like an open circuit, and y at 0 minus is going to be 0 volts. If I look at this condition here, y at 0 is equal to k1 e to the minus 0 over tau plus k2. E to the 0th is 1, so y of 0, which is 0 volts, is just equal to k1 plus k2. That gives us one of the equations that we need to solve for the constants in our solution. Now let's look at the final conditions, or the steady state conditions. This is as t goes to infinity. So the circuit as t goes to infinity looks like this 2 amp source. The switch is in this position. There's a 6 ohm resistor here. This capacitor, as t goes to infinity, if the forcing function is constant, will look like an open circuit. So there's no current through this side here. There's a 3 ohm resistor. So if there's no current there and I do KCL here, I know that there's 2 amps going through here, and the voltage across this resistor is going to be 12 volts, which is going to be the same as the voltage across these terminals. So y at infinity is equal to 12 volts. From the form of our solution, this is k1 e to the minus infinity over tau plus k2. E to the minus infinity is 0, so k2 is equal to 12 volts. If I use that up here, that means k1 is equal to negative 12 volts. Now we just need to plug the numbers into our solution. So let me clear up my diagram a little bit. I don't need the circuit schematic anymore. So in here, y of t is going to be k1, so minus 12 e to the minus t over 18 plus 12, or 12 times 1 minus e to the minus t over 18 volts for t greater than 0.